This is Math 261, Section 13.5 on the chain rules. Now that we've done functions of multiple variables and partial derivatives, there are different chain rules that apply in different types of situations. The first type of situation is where we have x and y are both functions of t. X equals g of t and y equals h of t. And so this would be the case like in the motion of a particle in two dimensions. You'd have a point x comma y, the position depending on time. So x would be a function g of t of time, and y would be a function h of t of time. And then you have a function w, which is a function of x and y. So you have w of x comma y. So that could be like the temperature of this particle. It's moving from this position, moving around, and its temperature is changing as it does due to heat sources or something. So for example, this is an example of where this type of situation comes up. W of x comma y might be the temperature at position x comma y, and then the position x comma y in turn depends on time. So this would be an example where this type of situation would come up, and then to find the derivative of w, dw, dt, this is the chain rule that we would use. So what is this chain rule saying, and how does that work? So in this type of situation, we want to take the derivative dw dt. We do that by taking the partial of w with respect to x times I'm going to say the word, quote, regular derivative, dx dt. You see, x is a function of t, so regular means like calc 1 or possibly calc 2 derivative, dx dt, plus the partial of w with respect to y times the, quote, regular derivative dy dt. So a lot of this becomes keeping track of when you're doing a partial derivative, when you're doing a regular derivative, and when you are doing a partial derivative, what is the variable that you're differentiating with respect to? So let's dive into this example here. Find dw dt using the appropriate chain rule, which is this one. W equals x squared plus y squared. X equals 4t, y equals 2t. And then we'll ignore this value, t equals 2, for a moment. At the end, we're going to plug that in and see the actual value of the derivative when t equals 2. But for now, we want to use the formula. So I realize it's right above us, but I'm going to copy the formula over here. The partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt. Now we have to go for it and do all these things here. First of all, the partial of w with respect to x. So this is an example of what I was mentioning before. You really have to keep track of what you're doing at a given moment and what the variable is. X is the variable now. So the partial of w would be 2x plus 0. The derivative of x squared is 2x. The derivative of y squared is 0 with respect to y. So this would be 2x times, now comes dx dt, which is the regular derivative of this. X equals 4t, so that would be times 4. Plus, now comes the partial derivative, partial of w with respect to y. So w is x squared plus y squared, but now y is the variable and x is constant. So the derivative of x squared is 0, and the derivative of y squared is 2y in this partial derivative. So this is 2y times dy dt, and y is here, y equals 2t, so the old-fashioned, quote-unquote, derivative of that y equals 2t is 2. So we have 8x plus 4y. Now that's an answer. It gives the value of the derivative dw dt in terms of x and y. So going back to like our temperature example, if we have the position the point is located at, we can plug into this to get dw dt based on x and y. And sometimes that was what we want, so that's why I say an answer. But also the reason I said an answer, not the answer, is because you could take this further and express it in terms of t, because both x and y are functions of t. And usually that's actually what we want to do. It's not always exactly the case. Sometimes it is left in terms of x and y, but generally we want to go all the way to t. So what I mean by that is now we have 8 times x, but x is equal to 4 times t. So this is 8 times 4t, plus we have 4 times y, but y is equal to 2 times t. So in terms of t, we get, what do we get? 32t plus 8t, which would be equal to 40t. So as a function of t, that is the derivative dw dt. Okay? And that's evaluating the derivative. Now we want to take this value t equal 2 and plug it into that. Of course, that's easy to do, and notation for that would be the same as the old notation for plugging in a value. When you use dw dt notation, you put a vertical bar like this, then you put t equals 2 to say, okay, I'm going to plug t equal 2 into that, and that's going to be 40 times 2, which would be 80. Of course. So in the homework problems for this, it would be very similar as to find this and then plug a number in. Here I've taken it just a little bit further to really try to relate it to, the situation of what's going on in terms of x and y depend on t, and then w depends on x and y, and this gives us a way to figure out dw dt. And like the typical example is a temperature of a point that's moving in 2 dimensions. So just in those terms, this particular question is not phrased really in those terms, but it's conceptually a good way to think about it. So I've just figured out to have specific numbers to think about everything at t equal 2. So x is equal to, this is the formula for x, go back and look at it, 4 times 2 is 8, y equals, the formula for y, 4. So this point or particle move in motion is at this particular moment, t equals 2 seconds, it's at the location 8, 4. And then there's this function w that depends on x and y. W equals x squared plus y squared, I think. I better go look back at that. Yep. Okay, so that's equal to 8 when t equals 2. So that would be like saying, if we're going to use the concept of the temperature function, the temperature of the particle at that moment in time is 8 degrees, whatever. This is just a concept example, so 8 degrees, whatever units. And the rate of change in temperature, see, that's what the chain rule and getting the derivative enabled us to calculate. It was 80. So just concept-wise, that's how to think about this. Not that this particular example was set up to actually represent temperature, but that's a typical type of example of this situation. Here's example 2. So we have a function w equals x times the sine of y. So w is a function of x and y. And x is a function of t, x equals e to the t, and y is also a function of t, y equals pi minus t. So x equals g of t and y equals h of t. the appropriate chain rule in that situation is this one for the derivative dw dt, the one from example 1. So we have dw dt, the derivative of w with respect to t, is equal to the partial derivative of w with respect to x. So we have to do that. So the partial of w with respect to x. So now x is the variable, y is a constant. So the sine of y is a constant. So this is like the derivative of x times 5, if you will, which of course would be 5. So here this would be the sine of y. So we have the sine of y times dx dt. Now x is equal to e to the t. So dx dt is equal to e to the t. E to the t derivative is e to the t. And we come along and we have plus the partial of w with respect to y. So here's our w equals x times the sine of y. Now y is the variable. X is a constant. So x comes down times the cosine of y. Derivative of sine is cosine. X cosine of y. So this is x cosine of y times the derivative dy dt. And y is pi minus t. So dy dt, derivative of pi, of course, is 0. Dy dt is -1 times -1. So this is equal, or dw dt is equal to e to the t times the sine of y minus x cosine of y. So that is a formula for dw dt. It involves t and x and y. And we want to take it to where it involves t, in terms of t, and simplify it. So we have formulas for x and y. They depend on t. So x is equal to e to the t and y is equal to pi minus t. We now plug in. And we get dw dt equals e to the t times the sine. So y is equal to pi minus t. Sine of pi minus t. Minus x, which is e to the t, times the cosine of y again, which is pi minus t. And then to take this a little bit further in terms of simplifying, a couple of trig identities rear their head. Sine of pi minus t and cosine of pi minus t are these identities. Sine of pi minus t is equal to the sine of t, and cosine of pi minus t is negative cosine of t. So using those, we can go dw dt equals e to the t times the sine of t minus e to the t times negative cosine of t. And so, final thing, these two negatives mean that the answer is dw dt equals e to the t sine of t plus e to the t cosine of t. And you could factor the e to the t out, but generally it's either way is fine. Either really factored out or not is not better or worse. So those two examples are, I'm going to call them type 1 problems, because we have this business about use the appropriate chain rule. We've only done one so far, but in the next video for this section, we'll do the other one. And part of this is recognizing what is the appropriate chain rule. So we've done this chain rule. And when is it, quote, appropriate? It's appropriate when we have this situation that I've been talking about with, we can think about it as a temperature. You have a particle, so or you can imagine it as a particle at location x, y, where x and y depend on t. And then a function w, which depends on x and y. So w depends on x and y are both functions of t. When you have that situation, that's when this is the appropriate chain rule. And that's what we've had in these two examples.